All right, let's go ahead and start. Please take out your notes briefly here at the beginning of the period before we get to the main subjects of today's period, which are actually 2 lab exercises. And we'll get to that a little bit later on. Let's consider the following interesting scenario. Consider a non-rotating, spherically uniform Earth. Dig a shaft from one side of the Earth to the other, passing through the center. Show that an object dropped in will execute simple harmonic motion and find the period of the oscillation. We'll assume that the shaft is a perfect angle. So imagine doing this. You go home tonight, you get out a shovel, you dig a hole, you go all the way through the Earth out the other side, you end up probably somewhere in the Indian Ocean. You go all the way through the Earth out the other side, you take an object, you drop it into the hole, show that it executes simple harmonic motion, and find the period of the oscillation. So how do we even begin to go about thinking about this problem? How do we actually show that it is in fact a simple harmonic oscillator and calculate the period? Well, what we'll do is after we set up F equals ma, we'll show that we end up with, kind of like we did with the simple pendulum, an equation that basically looks like the following. Okay, here's our comparison. Remember, of course, when we went through the dynamics of simple harmonic motion last time in class, for the simplest case of a mass attached to a spring, when you apply F equals ma to such a situation, you end up with the following differential equation. Like so, basically, constants times position equals acceleration, second derivative of position with respect to time. When you end up with an equation that looks like this, it is a simple harmonic oscillator equation. And then if you also recall from last time, the square root of the constants here that appears in front of the position, that's the angular frequency omega. We not only saw this basic form for the mass attached to the spring, we also saw something similar, if you remember, for the simple pendulum last time in class as well. What I want to show is that, in fact, for this situation, you end up with an equation that basically looks like this when you apply F equals ma with the law of universal gravitation to the situation. And then from there we can figure out ultimately what the angular frequency of the motion is, and then therefore the period. Now here's how we begin to think about it. Okay, so consider this Earth that's greatly simplified in the problem, like so, and you dig a shaft from one side of the Earth to the other, like so. And now let's just first of all consider what happens at the center of the Earth. So if you're at the center of the Earth, what do you suppose would be the net force of gravity acting upon you due to this symmetrical distribution of matter all the way around you in 3 dimensions?
Yeah, 0.
Yeah, it'd be pretty obviously equal to 0. So you would actually be weightless at the center of the Earth itself because the volume of the Earth is evenly distributed around you in 3 dimensions. So then therefore, as you move away from the center of the Earth, the force of gravity acting on you is going to increase. It will then reach its maximum amount when you're at the surface of the Earth itself, and it will then decrease from there as you move away from the Earth. So without going through all the gory mathematics necessarily, just qualitatively, that's how the force of gravity is going to behave. So how do we then begin to describe this mathematically? Well, let's consider our object of mass m here, some distance r away from the center of the Earth. And as I said a few moments ago, at the center of the Earth, the force of gravity would be 0, and then therefore as you move away from the center, it has to increase. The reason why it increases is for the following. Okay, imagine a volume like so, a spherical volume of radius r, where r, once again, is just some distance away from the center. contained within this an imaginary volume here is a fraction of the Earth's total mass. Let's call it m fractional. As you move away from the center of the Earth, the amount of m fractional, as I'm calling it, increases. Therefore, the force of gravity acting on the object due to this fractional mass of the Earth increases. So without going through all the necessary mathematics, the way that this behaves mathematically is that as you move away from the center of the Earth, it's as if you're containing within this imaginary volume more and more mass of the Earth. This then means that the force of gravity will increase, that is, the force of gravity acting upon the object. So that's how we start to think of F equals ma in this situation. Now, immediately beginning to also think of this in terms of oscillators. Picture the center of the Earth as being analogous to an equilibrium position, and the force of gravity then, therefore, acting upon the mass m, acts back towards the equilibrium position. So like we do with the spring force, which we think of as a negative, a restoring force, we think of the force of gravity here as a negative as well. So kind of keeping all that in mind, here's then how we set up F equals ma. We have, first of all, the force of gravity acting upon this mass due to this fractional mass of the Earth, which looks like this, gmm over r squared, equals then mass times acceleration. The mass of the object multiplied by the second derivative of position with respect to time. Like I said a few moments ago, by analogy, we think of the force of gravity here as analogous to the spring force. It's a restoring force, hence a negative sign. Okay, so this is how we begin to set up F equals ma for this situation. As is always the case with gravity, the mass of the object itself cancels out. So now let's kind of compare what I have here at this point to what we're basically trying to get with our comparison. Remember, with our comparison, it's basically constants times position equals second derivative. Notice that I don't quite have that here. So this equation is not an equation for a simple harmonic oscillator as of yet. So how do I make this look like this? Well, this is where the density of the Earth itself now becomes important. Now, density, remember, is just a definition. It's always given the Greek letter rho, and remember that by definition it's mass over volume. The density of the Earth, in this case, can be thought of as this fractional mass that's contained within this imaginary brown sphere divided by the volume of the brown sphere itself when it has radius r. So density as mass over volume, I'm going to write as the fractional mass that's contained within that imaginary blue sphere, or brown sphere, excuse me, divided by the volume of that brown sphere. Like so. And now what we do is just cross multiply a little bit, get this m fractional, and then plug it up here into my differential equation, and then we'll kind of see what happens. So I'm going to take this term here in the denominator and move it up to the left-hand side to get now this fractional mass of the Earth by itself, which then therefore looks like this. And then I take this expression and I plug it in here into my F equals ma equation. So when I do now, watch what happens. First of all, I have negative g over r squared. So, and then multiplied by this fractional mass, which is this quantity here. 4/3 pi times the density times r cubed equals then the second derivative up on the top board on the right hand side. Once again, that's just the acceleration. Okay, notice that a little bit of cancellation happens. And r squared here, and then r squared here. And if I just kind of clean up what's left over, here's then what I get. Now let's compare this differential equation, what we already know from the top board. So from the top board, remember it's stuff times position equals second derivative. Simple harmonic oscillator, square root of the stuff is the angular frequency. Notice that we have the same thing here. Stuff times position equals second derivative. So yeah, it is a simple harmonic oscillator. If we dug a shaft all the way through the Earth in this manner, dropped in an object, it will execute simple harmonic motion. And then we want to, lastly, calculate the period. We can find the period because remember that the angular frequency omega is always the square root of the constants here in front of the position. So then therefore for this problem, it's going to be the square root of this stuff right here. So the angular frequency of the harmonic motion is the square root of this, like so, where then it asks us in the problem to calculate the period. So the period is 2 pi divided by omega. I'll just go ahead and plug it here into the denominator and leave it at that. Like so. And then therefore, when I plug in all of the numbers here, I'm going to end up with the period in terms of seconds if I use the correct units. So now we get to the numbers themselves. Now the first number that we need is the universal gravitational constant from chapter 6. It's been a little while since we've seen it. Remember that the universal gravitational constant is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. But then we also need density of the Earth. So how do we calculate the density of the Earth? Well, now what we do is we think of the density of the Earth as the total mass of the Earth, here in green, divided by its total volume. Let's think of the density that way. Total mass divided by total volume. And we've seen the mass of the Earth and the radius of the Earth in previous examples, back in chapter 6, for example. So the mass of the Earth, we worked with it in several problems back then. 6 times 10 to the 24 kilograms. And the radius of the Earth, we've been working with that on and off over the year. 6.4 times 10 to the 6 meters, that's 6,400 kilometers. So at this point, I'm going to give my calculator a workout. I'm going to calculate the density of the Earth. When you do it in this manner, by the way, total mass over total volume, you're basically calculating the Earth's mean density. So the Earth's mean density is then therefore the following number. It will be, by the way, in terms of kilograms per meter cubed. So mass of the Earth first, and then divided by quantity, 4/3 times pi. 4 times pi, there we go, 3. And then multiplied by the radius of the Earth cubed. Raise that guy to the 3rd power. And this ends up being 5,464 kilograms per meter cubed. This is the Earth mean density. It's about 5,500 kilograms per meter cubed. I'm going to take that number and now plug it into here and multiply out by the other stuff as well as G to eventually now get the period in terms of seconds. So let's see what I get. So I still have the row here in my calculator. So now just times G, I'll do it that way. And then times 4 times pi over 3, square root all of that stuff. Take the reciprocal to then multiply by 2 pi. And then in terms of seconds, you end up with about 5,085 seconds. So this would be the period of the oscillation. So then exactly how big is that? Well, there's 60 times 60 or 3,600 seconds in an hour. So if I divide that by 3,600 seconds in an hour, I end up with a number that we've seen before. It's 1.4 hours. We've seen this number about the Earth twice before. We saw it first of all back in chapter 5. In chapter 5 we did an example involving centrifugal force where we took the Earth and spun it faster and faster and faster such that everybody at the equator becomes a projectile and ends up in orbit around the Earth while the Earth is rotating with them. In order for that to happen, the Earth's rotational period would be 1.4 hours. Then in chapter 6 we did a problem involving an orbit, an object orbiting the Earth in uniform circular motion at a low altitude above the ground. It takes the same amount of time to go around, 1.4 hours. So why is this number here for the time for the oscillation the same as the time for an orbit? Because in both cases it's the exact same force. It's the force of gravity. And also remember, and I've said this now a couple of times, that the two-dimensional motion of uniform circular motion and the one-dimensional motion of harmonic motion are very closely related. Basically, the harmonic motion is just one component of the overall two-dimensional motion. So then therefore, the time should be the same. So if it takes 1.4 hours to go around the Earth, then therefore it's going to take 1.4 hours to complete one oscillation. So if we did this here in this classroom, someone could jump in, they would come back before the end of the period. They would take about 1.4 hours, or about 85 minutes for you to go all the way to the other side of the Earth, and then come all the way back, completing one oscillation. Isn't that cute? All right. Nice little challenging problem with a very interesting result. I suggest you wear a crash helmet and goggles. All right, let's get to today's lab exercise.